Hi everyone, in this video we're going to do some more Lagrangian mechanics. So last time we looked at a system where there's a pendulum with a massive sliding support that's free to slide backwards and forwards along some kind of rod. This time we're going to look at a very similar system, but instead of allowing the support of the pendulum to oscillate freely backwards and forwards, we are going to apply some force and, well, force it to move backwards and forwards sinusoidally. So the diagram here shows the setup. We've got all the standard parameters: mass of the bob, m, length of the rod of the pendulum, L, angle made with the vertical, theta, and this A cos omega t here, that's just the horizontal displacement that we're forcing the support of the pendulum to have. So A is the amplitude of the forced oscillations and omega is the frequency of the forced oscillations. So the goal is simply to figure out how theta evolves as a function of time. There's only 1 degree of freedom in this problem as opposed to the last one in which there were 2 degrees of freedom because we allowed the support to slide free. So just 1 degree of freedom. And well, let's get started. We need to know that the Lagrangian is T minus V, kinetic minus potential energy. As we did last time, we want to write down the Cartesian coordinates of the mass. Here, the only mass involved is the bob of the pendulum. The x-coordinate of the bob of the pendulum, in other words, just the horizontal displacement from some reference point, well, you've automatically got a horizontal displacement of a cos omega t from the support. So let's just write that down. A cos omega t. You're going to have an additional amount of, well, that much, the line that I've just added to the diagram, using trigonometry, that is L sine theta. So x is a cos omega t plus L sine theta, and y, it's going to be negative, or it's going to be a minus sign, because we're going to put our origin of our coordinate system up here, and the pendulum is hanging down. So we get a minus sign, and it's simply this far below the support, again using trigonometry. That's L cos theta. So y is minus L cos theta. Because we're going to need to write down the kinetic energy, we need the time derivatives of those as well. So x dot, the a cos omega t has a time dependence, so we differentiate that to get minus omega a sine of omega t. Then to differentiate this L sine theta, we've got to use the chain rule, and we get a plus L theta dot cos theta. Similarly for y dot, we just get L theta dot sine theta. So we're now ready to construct our Lagrangian in terms of theta. Let's do the kinetic energy term t first. It is, of course, half mv squared. So we've got our half mv squared is just x dot squared plus y dot squared. So we square both of those expressions. When we square x dot, which is all of that stuff, we're going to get 3 different terms. You're going to get the first term squared, which is omega squared, a squared, sine squared of omega t. You're going to get the cross term, which is minus 2 omega al theta dot cos theta sine omega t, not the nicest looking term, but just coming from doing that times 2. And then you've got your final term squared, which is plus L squared theta dot squared cos squared theta. Then that takes care of the x dot squared bit. We're going to have to add on the y dot squared. Y dot squared is simply L squared theta dot squared sine squared theta. So what about the potential energy term V? Well, it's just gravitational potential energy, mgy, and we know that y is minus L cos theta, so that's straightforward. V is minus mgl cos of theta. So let's just write down our full Lagrangian and make a couple of simplifications. I'm going to expand the brackets in the t term, so you have a half omega squared a squared sine squared of omega t. You've got the half cancels with the 2, so you've got minus m omega al theta dot cos theta sine of omega t. Something nice happens with the last 2 terms. You use the fact that cos squared theta plus sine squared theta is 1, and you just get L squared theta dot squared, so that becomes half m L squared theta dot squared. Then you subtract off the potential energy term, minus becomes a plus, and you get plus mgl cos theta. So there's our Lagrangian. Now we've just got to use that to get the equations of motion. I said equations of motion. I guess I really mean equation of motion. There's only one because theta is the only degree of freedom here. Of course, we are going to use the Euler-Lagrange equation in theta, so d by dt of dl by d theta dot minus dl by d theta is equal to 0. So we've got to differentiate the Lagrangian with respect to both theta dot and theta. So let's go ahead and do that and plug it directly into the Euler-Lagrange equation. So we've got d by dt of, take this expression for L, differentiate with respect to theta dot. This term involves theta dot, that term involves theta dot. So we're going to have to differentiate those two. That's fairly straightforward though, because this term here, the theta dot just disappears when you do the differentiation. So we put there minus m omega al cos theta sine of omega t, and that term you just pull down the factor of 2 and reduce the power, and you get plus ml squared theta dot. What about the minus dl by d theta? So you've got theta dependence in that term and that term. Cos differentiates to minus sine, that cancels that minus sign there, so you get m omega al theta dot sine theta sine omega t. And then we've got to differentiate that bit, it just goes to minus sine, so minus mgl sine theta. All of that is supposed to be equal to 0. And now we've just got to expand the brackets, do the differentiation, and we'll have our equation of motion. I guess the first thing to do is cancel down a couple of parameters that are common to all terms. There's an m and an l in all 4 of the terms in that equation, so we can cancel those down. M, L, M, 1 power of L, M, L, and M, L. Then we're going to do the differentiation. For that first term up here, we're going to need to use the product rule because theta and sine omega t both have time dependence. So if we do the differentiate the cos theta bit first, that differentiates to minus sine theta, and we get a theta dot from the chain rule. That makes that minus sine disappear. So you end up with omega a theta dot sine theta, and you keep the sine omega t as it is. Second term in the product rule, you're going to differentiate the sine, and you get cos, and so you keep the minus sign this time. So you get minus omega. This time it's squared because you pull out an omega from the chain rule. So minus omega squared a cos theta, and then sine of omega t. No, we have to differentiate it. Cos of omega t. And then we differentiate the L theta dot term, which just becomes plus L theta double dot. Then we just add in the rest of the terms, expand the brackets from the previous line, and you've got minus omega a theta dot sine theta sine of omega t, and then plus g sine theta. That's all supposed to equal 0. You get a nice cancellation happening here. This term is the same as that term, so your equation of motion only ends up containing 3 distinct terms. We can just reorder the terms, divide through by L to put it into a slightly more recognizable form. You'll see what I mean in a moment, because if you divide by L, you get theta double dot plus g over L sine theta. This already looks like an SHM equation, which is not surprising really. And then we'll move this term over to the other side because it's kind of like a forcing term. Well, it is a forcing term. You're going to have omega squared a over L cos theta cos of omega t. So there's a fairly nice looking equation of motion. Again, we can't solve this exactly in its current form. We're going to have to make some approximations because of the non-linearity of that sign, and also because our forcing term on the right hand side itself depends on theta, which is a bit of a problem. So you could solve that numerically if you wanted to see the full solution, but for the rest of this video, let's focus on small oscillations. Assume that theta is much less than 1. Then you get theta double dot plus g over L theta is roughly equal to omega squared a over L cos omega t. We're saying cos theta is roughly just 1 because we want to get a linear equation of motion. The next term would be theta minus theta squared over 2. That's a higher order than we're going to be working to. So here we go. We want to solve that equation to see how theta evolves. It's basically a forced simple harmonic motion equation. It's a inhomogeneous ordinary differential equation. So we're going to have to split the solution into 2 parts, complementary function and particular integral. So let's go through that procedure. The complementary function, I'll just put CF here. it comes from solving the left-hand side equal to 0. And it's just simple harmonic motion. I'm not going to go through the full procedure there, but well, if you're watching this video, you probably already know the solution is a cos of omega naught t plus phi, where a and phi are constants to be fixed by the initial conditions, and omega naught squared equals g over L. The other part of the solution is the particular integral, and that comes from basically making an educated guess as to the functional form of theta that will make the right-hand side work out correctly. So because the forcing term is sinusoidal, it's proportional to cos omega t, we want to try a sinusoidal function. So let's call it b cos of omega t. You could, if you wanted to, include a sine contribution as well, but you can kind of see by inspection that the sine contribution has to be 0 because you've got a theta term here, and that's going to give you, like, if you included a sine term, you would have a sine term on the left-hand side, but not on the right-hand side. So we don't really need to include that there. There is no extra sort of phase in that cosine term. So what we do is take our trial solution for the particular integral, substitute it into the left-hand side, and figure out what this coefficient b must be in order to, well, make the equation work out correctly. So differentiate it twice and you get minus omega squared b cos of omega t. Then sub it in, well, directly in as the second term on the left hand side, you get plus g over L b cos of omega t, and that's of course supposed to be equal to omega squared a over L cos omega t. All of the terms are proportional to cos omega t, so we can just equate the coefficients, get rid of the cos omega t, and say that g over L minus omega squared has to be equal to omega squared a over L, or wait a second, I tried to factor out b, but I forgot to put the b in. There we go. And then we just divide through by the bracketed term to get b on its own. It is omega squared a over g minus omega squared L. So we can now write down our full general solution for theta as a function of time. It's the complementary function plus the particular integral. So theta is your a cos of omega naught t plus phi. Remember, omega naught is the square root of g over L. Then we have to add on the particular integral, omega squared a over g minus omega squared L times cos of omega t. So as always, we want to take some time to physically interpret our solution and understand what it's telling us. The first term is not really that interesting because it's just the usual free oscillation solution for the simple pendulum. It's the second term that I want to focus on, right? Because your solution is a superposition of the free oscillation and also this bit, which is coming from the driving of the support at the top. So it oscillates with the same frequency as the driving frequency. You've got this prefactor here, which is omega dependent, and that contains information about the amplitude and the phase of the forced oscillation. So what I want to do is sketch a graph of that prefactor of the forced term and talk a little bit about the shape of the graph. I've called my y-axis signed amplitude because amplitude usually implies, well, a positive quantity. This quantity here can be either positive or negative. When it becomes negative, that just means the oscillations are 180 degrees out of phase with the driving oscillations, but I'm kind of lumping that into a single quantity and calling it the signed amplitude. So how does this thing look as a function of omega? Well, when omega is small, you can neglect this minus omega squared L in the denominator, and you just get omega squared a over g, which is just a quadratic function. So the graph looks approximately quadratic for small omega. Something interesting happens when the denominator becomes 0, right? When omega squared is equal to g over L, the denominator becomes 0, and so the amplitude becomes essentially infinite. So we get a vertical asymptote on the graph at an angular frequency of the square root of g over L, which is what we earlier called omega naught. It's the frequency of free oscillations of the system. So if we just complete that first bit of the graph, it looks roughly quadratic, then goes up towards this asymptote. So there's basically a resonance when omega is equal to omega naught, when the driving frequency matches the natural frequency of the system. I'll also point out that this quantity is positive up until omega equals omega naught, and therefore the oscillations are in phase with the driving oscillations. As soon as omega becomes bigger than the square root of g over L, the sign of the denominator, and therefore the sign of the whole signed amplitude term, becomes negative. So the graph suddenly ends up down here. What's going to happen for very large frequencies? Well, when omega is very large, you can neglect the g, just the g, not the minus sign, and then the omega squares will approximately cancel from the top and the bottom, and you end up with a horizontal asymptote on your graph. So the overall shape ends up looking something like what I've just sketched on here, and the value on the y-axis at the horizontal asymptote is going to be minus a over L, right? Just imagining, ignoring the g term and cancelling the omega squared terms down. So let's mark that on as minus a over L. I should also mark on that because the graph has become negative, the oscillations here of the pendulum are in antiphase with the oscillations that are driving the system. So a few comments to make about this graph. Firstly, obviously in reality, the amplitude is not going to become infinite. One problem is that we have neglected damping in the system. Damping would reduce the amplitude at resonance, stop it from being infinite. Aside from that, we also have the problem that we assumed, remember, that theta is much less than 1. At resonance, that's definitely not the case. You're going to have large oscillations. So our analysis kind of breaks down close to resonance, but you would still have the same key feature that the amplitude becomes very big and then suddenly changes its phase once you go past omega naught. Finally, is there any significance to this minus a over L? Well, if theta is oscillating with an amplitude of a over L, another way of saying that is that the quantity L theta is oscillating with an amplitude of a. Now, L theta is approximately L sine theta, which is this little horizontal distance up there. And so when theta is oscillating with an amplitude of a over L, the horizontal distance traveled by the bob is exactly opposite to the displacement of the support of the pendulum at that particular moment, right? So if the support has moved 1 millimeter to the right, then the bob is 1 millimeter to the left. So at very high frequency, it's oscillating in such a way that the center of the rod of the pendulum is staying fixed, right? Because the bob is moving left by exactly the same amount that the support is moving right, or vice versa. That seems fairly intuitive to me. So let's leave it there for this video. Thanks for watching. I do have other Lagrangian mechanics problems that I've done in the past on my channel if you're interested in seeing some more similar stuff, and I'm intending to do more of these in the future as well. So I hope to see you soon.